Good afternoon, everyone. Welcome back to E304. In today's lecture, we're going to continue our discussion of energy levels and density of states. So in the previous lecture, we discussed the density of states equation, and that was ds of E, and we said that was per density of states, so per unit volume, per unit energy. We also talked about the Fermi-Dirac equation, which gave us the probability of an electron occupying a state. And we went from that on to find the number of electrons per unit volume, per unit energy that we have available for conduction. So we took and we multiplied this probability of occupation by the density of states. Okay. And then we took the integral of that from 0 to the Fermi energy. Okay, and we said that all this happened at T is equal to 0 Kelvin. So because of that reason, the probability is always equal to 1 that an electron is found below that Fe Fermi energy. And this is, of course, dE. So this all boils down to tell us that the concentration of electrons has to be equal to the integral from 0 to Fe of the density of states of E dE. Well, when we take that integral, we come up with this equation that gives us a concentration of electrons. So little n means concentration, and the sub E means of electrons. Well, we see that in this equation we have E sub F, so let's solve for that. We solve for E sub F in that equation, and we get that our Fermi energy is a function of H and mass and concentration of electrons, and this is the only variable. H, of course, is a constant, M, of course, is a constant. So really, our Fermi energy is proportional to the concentration of electrons, or the number of electrons, so big N sub E is the number of electrons, over the volume. So this is a very important conclusion. The Fermi energy is proportional to the number of electrons divided by the volume. All right, so now let's think about the separation between energy levels. Okay, so delta E means separation between energy levels, and that is approximately equal to the Fermi energy divided by the number of electrons. And this is true that if we say that all the energy levels up to the Fermi level are filled. Okay, so if everything is filled up to the Fermi level, then if we divide the Fermi level by the number of electrons, that should give us how far apart they are. All right, so if we substitute into this equation the equation for E sub F that we had on the previous slide, and that was that E sub F is equal to NE over V, then the NE's cancel, and we get the conclusion that the spacing between energy levels has to be proportional to 1 over the volume. And the importance of this conclusion here is that basically what we're saying is that the smaller the volume of our material is, the bigger the spacing between energy levels. So let's look at what this means. If we have a solid with a large volume, many atoms, then as we've seen in the past, the energy sublevels split many times, and essentially you have an energy band because these splits, there's so many of these splits and they're so close together you can't even distinguish them. Well, if we take this volume and we make it much smaller, let's say just a few atoms, let's say 13, then we begin to see that there's 13 splits, and the delta E, the spacing between the splits, starts getting a little bit bigger. And as we get to smaller and smaller particles, then the splits get even farther apart, so the delta E's get even bigger. So as the volume is decreasing, the delta E is increasing until we get to just one atom, and of course one atom has no splits, it just has the one sublevel. Okay? So these delta E's, these gaps between the energy levels, get bigger and bigger as we get smaller and smaller particles. All right, well, what does that mean, and what's the useful application of this? Well, let's talk about quantum confinement and quantum structures. So if we have a large volume, a bulk, we can start to confine an electron, or try to confine an electron in this large volume. So we can confine it in the x direction, the y direction, and the z direction. So if we confine, let's confine its width here. And then we have what we'd call a quantum well. If we confine it in two directions, we confine the width and we confine its height. Then we have a quantum wire. And if we confine all three of the dimensions, we get a quantum dot. So in this large bulk volume of material, we can somehow, if we can somehow confine an electron to a specific area there, then we can see that the electron density and the density of states become more and more discrete as we have higher and higher confinement. Okay? Until in a quantum dot we can see that the density of states is indeed discrete, and the electron concentrations are very specific here. So what's a small enough confinement? How small is small enough? Well, to figure that out, we need to consider the wavelength of an electron. And we know that the wavelength of an electron is equal to h over p. So the dimension of the quantum dot should be comparable to this wavelength. But in what way? If we remember the potential well from chapter 3, I believe, we might remember that the width of that well was given as L, and the boundary condition was that, okay, the probability has to be 0 that that electron exists outside of the well. So in order to confine it within the well, the width of that had to be equal to lambda over 2. So the period of the function over 2, or the wavelength of the electron divided by 2. Okay? So let's take a quick example. So the example here is to estimate the minimum diameter of a quantum dot that can confine a 7 electron volt electron. Okay, well, energy is equal to 1/2 mv squared because it's an electron, right? So we can calculate calculate its energy. That means that V is the square root of 2e over m. So we can plug in 2 times the E, which is given to us as 7 electron volts, and multiply that to get the right units of coulombs, divide by the mass, and we get that the velocity is 1.56 times 10 to the 6 meters per second. All right, so now we can look at lambda. We know lambda is equal to h over the momentum. Momentum is mass times velocity, so h over mv. We know h, it's a constant. We know m because it's an electron. And we just calculated v, so we can calculate the wavelength of that electron. The wavelength of the electron turns out to be 470 picometers. So the well has to be at least half of that, so at least 235 picometers is how big is the smallest that our quantum well or a quantum dot must be in order to confine this particular electron.